Okay, so now what we're going to do is look at one of my favorite questions about a Ferris wheel. Um, because it's interesting to start thinking about the fact that things that go around in a circle can be modeled with a trig function. Because often, we see the trig function as moving forward and going in this nice little wave function. But it's all based on going around a circle. So we've been studying the angles going around a circle, all the way to 360. And of course, it translates to a sine curve, but we often don't really think about that. So what we want you to do is imagine a Ferris wheel and imagine a person sitting on a Ferris wheel and what their travel looks like. So they get on the bottom, of course, and then or they might get on someplace else, but they get on the wheel and then they go up and then they go down. And the graph itself keeps moving forward because time is the independent variable. So there's a couple of online demonstrations of this that I'll show you. So here's just a stagnant one, but you see there's the person getting on, and then you see so if we pretend they got on right here, you see that they start going up, and then of course it just continues up here, and then to a highest point, and then they come down, and then they go back up. So this is them going around the Ferris wheel, but you see it goes from the highest point, so maybe they get on here in the bottom, and then they go up and to the max, and then down to the lowest, and then up to the max, and we see that. There's another example here. So there's the person, they're on the wheel right there, and you see their height is being graphed, and of course there's a sine curve, perfect sine curve right there. But there they are, maybe their person sitting here and they're on the Ferris wheel there, they get on to the lowest point, and then their graph, they go up, and they get to a highest point. And it's almost like you pause there. You know how you're at that highest point in the Ferris wheel and it's like you're standing still? Well, of course you're not standing still, but there's a long period of time when you're at the highest point. So it feels like you're up there for a while. So here we are again, we're up here, right? And you're virtually at the top, and you see how it feels like you're pausing because there's this stretch here where you're at the highest point and then you come down. You're not really pausing, it's just you're at a high point. It doesn't feel like much different, and then you stay at that high point for this long little period of time, and then you go down, and then the same thing down at the low point. Okay? So those are just two visual animations to really talk about what we're doing, but we have the stagnant observation here on this graph. So we're going to try and model a person riding this Ferris wheel, and eventually we want to know how long was the rider 30 meters above the ground. So during one revolution, how long was the rider 30 meters from above the ground? Because the most fun part about the Ferris wheel is at the top part. And so, 30 meters is going to be up here. So we want to know how long is our rider up there. This part isn't quite as fun in the bottom, this is when people get on and stuff and so forth. But the fun part is up here in this top part. So we want to be curious in this particular ride, how long are people up there? So that's something I'd like to know about. So we're going to read the rest of this. So a Carnival Ferris wheel with a radius of 20 meters. So a radius, so that means from here to any edge on the outside is 20 meters. It makes one complete revolution every 16 seconds. So it takes 16 seconds to do a full revolution. It says the bottom of the wheel is 1.5 meters above the ground. Okay, just so it doesn't scrape along the bottom. So you probably step on a platform. We want to know how long the rider is 30 meters above the ground. Okay, so what we have to do, the difference between today's question and the ones from yesterday is, we all had all the data. Today we got to interpret the data and get the data from the information. So I'm going to do that by making a little chart over to the side here. So this is time and this is hours, or height, sorry. So let's consider the 0 spot. So the 0 spot is right down here. And the height is, well, you're 1.5 meters above the ground. Okay, so you step into the ride, you're 1.5 meters above the ground. Okay. We know that we're going to go from here and then ride all the way around the outside of the wheel, and then 16 seconds later, we're done. Or one revolution. But I'm going to start imagining, I'm going to break that ride, that 16-second ride, up into 4 intervals. Where are we at 4 seconds, at 8 seconds, at 12 seconds, and 16 seconds? Of course, you can start to see that I picked 16 seconds as one revolution on purpose, so it would break up nicely. So let's look at halfway. Actually, what we know at 16 seconds, we're back to 1.5. Right? We know that a full rotation, 16 seconds later, we're back to 1.5. But I'm interested in where are we halfway? So on the picture, we've gone from here, and we've gone all the way up around, and we'll say we're at this spot now. Okay? So how high is that? Well, we know that this from here to here, and from here to here is going to be the same. It's going to be 20 meters and 20 meters. Plus the little extra 1.5 meters off the ground. So if I was to redraw that, because I'm sort of outside the circle there, I've got 1.5 meters here, another 20 meters of radius, and another 20 meters. So at the top here, I'm at 20 plus 20 is 40, plus the extra 1.5, so 41.5 halfway. And then I understand we can figure out this when you're at this spot right here. Right here is the 1.5 plus just the 20. So it's at 21.5. And then you start coming down, so your height gets smaller, but at this spot right here, you're at 21.5 again. So if I think about this and follow this path, so I get on 1.5, I start to go up to 21.5, you know, half the way up, and then I'm at the highest point at 41.5, and then it starts going down to 21.5, and then come back down to 0, or 1.5 meters off the ground. So I'm going to take a second to graph that. I need to choose an appropriate scale, and you have the graph there. I'm going to choose a scale of by 2s on the bottom, so that would be 4, 8, 12, 16. So 2 ticks is 4 seconds. And then for height, I think I'll just go 2 ticks is 10. So 10, 20, 30, 40. And we'll start graphing this. So at 0 time, we start at 1.5, so just below or just above the 0. 4 seconds, we're at 21.5, so right here. 8 seconds, we're at the highest point at 41.5. And then back down at 12 seconds, it's back here. And then just above the graph there. And then, of course, this is going to repeat, right? It's going to come up, and another 4 seconds later, it's going to be back up here, back up as the highest point. And I'm just going to erase this spot here, because I don't want us to, I want us to always remember that we're not down at the very end. Okay. So this represents how high the rider is at various times along the graph. 16, 12, and then we start going 20, 24, and so forth. Okay, so our question says we want to know how high they are at 30 meters. Well, I could go off and actually measure that and take an estimate and figure out where these spots are. You know, one of them's going to be right about there, and then they're going to be below. So during one cycle, it's this spot above. But this would just be a guess on the graph. And, you know, that's fine. We should be able to come up with a more accurate representation. So we're going to do that by coming up with the equation. So just like we did yesterday, we're going to take this information and try and come up with the amplitude, the period, the phase shift, the vertical translation, get an equation, then do the math. So let's start with the amplitude. So the amplitude, this, highest and lowest points. Highest point is 41.5. Lowest point is 1.5 divided by 2. So that's 40 over 2 is 20. So we have an amplitude of 20. And when I stop and think about that now, of course it makes sense. Radius of the circle is 20, so you're going to go up 20, down 20, and keep going back and forth. All right, the period. Oh, by the way, I haven't even drawn a sine curve. I think a sine curve good spot for the sine curve is right here. That's what I'm going to try and measure. Starting here, ending here. Doesn't change the amplitude. The amplitude is still 20. The period. So the period is how long it takes to complete one cycle. Well, I know from the question it says during one revolution, or it takes 16 seconds to do one revolution. So obviously the period is 16 seconds. I can verify that on the graph. There I am at 4, and then at 20 I'm back to my starting point, so 16 seconds later. So the cycle is 16 seconds. Remember that the 16 is just the time. I need to figure out the k value. So 2 pi over something is 16. Do the same math as yesterday. 2 pi equals 16k divided by 16. And that's pi over 8, just reducing. So remember, as I said yesterday, the period is a regular number, so now your k value is a pi in it, as opposed to the questions we did last for the test, where all our periods were pi values and our k's were just numbers. Okay, so we've got the amplitude is 20, period is 16, so the k value is pi over 8. I just need a phase shift and a vertical translation now. So looking at this is my starting point. So I've obviously moved over 4. So let's move to the right 4. A vertical translation. Well, I don't need to guess. Yesterday maybe I was guessing on some of these, but here I know that vertical translation is right here. And remember, that's just above 20. Well, it's right here, isn't it? It's 21.5. So it's up 21.5 units. So I take all that information. And remember, when I said starting point, I mean starting point of this red function. Okay, not starting point in the ride. I know the ride starts down here, but I'm going to model the scenario from here because it looks like where the sine function goes. You could do this whole question again with cosine and start down here at the bottom. But I've chosen not to do that. I've chosen to do sine. So the starting point of our function is here. Maybe not our ride, but our function is right there. Okay, so I can take all this information now, come up with the equation. So instead of saying y equals, I'm going to say h for height. So h equals 20. It's the sine curve. The amplitude is 20. Sine. K value is pi over 8. Instead of x, I'm going to use t for time. This one moves right 4, so I'm going to go minus 4. And then up 21.5. So all this work, this is the hard part. Taking the scenario, reading the information here, understanding the picture, and coming up with the table or the graph. Those are just meant to help you so you can come up with the equation. The equation is the best representation of this scenario. Now I can use this equation to answer our question. How long are they up 30 meters? So the first thing I do is figure out this spot right here. The first spot where I hit 30 meters. So I'm going to sub in h equals 30. All right, so I'm going to have to isolate for t. So much like the questions yesterday, we got quite a bit of work to do. First thing I'm going to do is get rid of the 21.5, so subtract 21.5 from both sides. So of course that's going to leave me with 8.5 equals 20 sine pi over 8 t minus 4. Next I'll have to get rid of this by dividing. So if I divide 8.5 times 20, I should get 0.425. Oops. Okay, next I got to do inverse sine. Should get rid of that. So I punch that in my calculator. Remember, I'm in radians. Okay. Radians. So if I put inverse sine here, I'll get 0.43896, da 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 da. Next, divide by pi over 8. So in that case, it would be, again, this number is all on my calculator. It would be times 8 divided by pi, right? It's being divided by 8, so I got to multiply by 8, then divide by pi. That's going to leave me with t minus 4. I think if I punch that in my calculator, I get 1.1178 equals t minus 4. Last step, opposite of minus 4 is plus 4. So I add 4 to this and I get 5.1178 or so. So I'm just going to round that and say that that happens at 5.1 seconds. So what was all the math I just did? Okay, I'll give you a second to look at that. Hopefully your numbers are the same. So what was this math I just did? Well, I just went off and figured out that this spot right here is 5.1 seconds. And if I look at my graph, that seems reasonable. It's maybe, well, this is 6. Maybe it's not bad. It's close to 5. Okay. It is an estimate, so 5.1 seconds is an exact value. So that's great, but that doesn't answer the question. That just says that it's going to, at 5.1 seconds into the ride, I'm going to hit the 30-meter mark, someplace up here. That's great, but now I want to know how long I'm up there. So I'm up there from here all the way to this spot. There's the first spot at 5.1 seconds. Where's that? Well, on the graph, I can see it's right here. So the question is, how am I going to do that? Well, again, I'm going to notice that 5.1 seconds is from here to here. So if I work backwards from the lowest spot and come back, this should be at 5.1 seconds as well. 5.1 seconds. Except instead of subtracting from 1 like the last time, I'm going to subtract it from 16. So this one is going to be 16 minus 5.1, or 10.9 seconds. And that seems reasonable. That looks like a pretty good guess. 10.9 seconds. So if the first spot is 5.1 seconds and it stays up there, and the next time it's hits at 10.9, I know that I could subtract those and get how long I'm totally up there. So therefore, the rider is above 30 meters for, well, 10.9 minus 5.1, which is about 5.8 seconds. So now I can, if I'm the ride operator or something like that, I can say, well, for almost 6 seconds, the people are up there at the highest point, the best spot on the ride. The whole thing is 16 seconds, so 10 seconds they're either coming down or below, but at least for 6 seconds they're up at the highest spots, getting your best view or whatnot. Yeah, you can slow that down. You can make it longer by slowing the whole ride down. But you know that for at least that percentage of the time, we're up at the highest spot. Okay, so that's the Ferris wheel question.